Okay, so it's 15 past, so let's begin. Okay, so welcome everyone for this week's Machine Learning Coffee Seminar. So this week you have a very interesting talk by Dennis Muiruri on practice and infrastructure for ML systems. If you have any questions during the talk, you can just ask them right away. So you can either raise your hand or write the question in the chat. Okay, so Dennis, please go ahead.
All right, thank you, Markus. So good morning, everyone. My name is Dennis Muiruri, and work as a researcher with the Empirical Software Engineering Research Group at the University of Helsinki. And today I have the privilege to present to you a work that we did earlier in the spring this year. And we call it Practices and Infrastructure for Machine Learning Enabled Systems. What I think I've set out to do today is give you a bit of the research background, basically what we were looking at, or let's say the backdrop of our research, and then briefly just give you a small introduction to our methodology for research purposes, or the completeness of the work. And then I'll just demonstrate maybe the cases that we studied. We have 16 cases that we had. And then we'll probably spend most of our time looking at the results. And by this, I mean just exploring the sort of tools, the frameworks that we encountered during this study. And most importantly, the sort of practices and challenges that were demonstrated by the practitioners that we spoke to. So what was our motivation, or what was the background of our work? And this started by noticing that if you look at most of the studies that are published in terms of machine learning infrastructure, we noted that usually these are done by very big companies. They're very experienced, they're large in terms of computing resources. And so we thought that there was a gap that we could academically at least plug by looking at other kinds of organizations, other kinds of size of organizations, different domains, and so on. And so that's what we set out to do. And why this is important is because if you look at big companies, we're talking of Google, Facebook, and so on, when they publish their papers, usually it's very hard to, let's say, for a typical company to relate with what they're talking about, or let's say to replicate what they're talking about. Maybe that's a better way of putting it, because usually they have custom hardware, usually even dedicated hardware for different types of tasks. So if you're looking at data workflows, machine learning workflows, some of them go to the extent of having customized hardware for doing those different parts of the stack. And usually they have global infrastructure, which is distributed in different geographic locations. Usually their training frequency tends to be quite high. You're looking at even daily training frequencies. And usually they tend to use multiple frameworks across their machine learning pipelines, and we will revisit this later on. So this is just to show you what of sort of the setups that are used in big corporations, and we will see a lot across this sort of presentation that in some cases this doesn't match what you find in typical companies who have machine learning, or let's say AI related products. So our work then is to really provide empirical evidence of sort of what practices are used and what of sort of infrastructures are used by a wide range of companies that would not fit into those big tech companies, but nonetheless have machine learning related products. A bit of context, why are we doing what we're doing? And that starts by looking at this image in the left. When we're talking to data scientists or anybody who deals with data science, your work mainly relates to collecting data, preparing it, and training the models, and then evaluating, and you keep iterating along this cycle. So what we are trying to do at the research group level is trying to broaden this perspective by looking at the bigger picture, that once you get your model trained and you have your parameters tuned to your taste, then you need to start to think about how to productionize your model. You have to consider what sort of inference systems you're going to put in place. How do you monitor your models? Do you collect any metrics that allow you to continue to monitor the health of the model? And of course, look at whether the business needs have changed as you continue to deploy and train your models. So this world is what we call probably MLOps. And that's our interest within this interview setting. So if you think in terms of methodology, I've already indicated that we conducted interviews with practitioners, and these interviews were semi-structured. This means that when we're talking with the practitioners, we don't really insist on a very structured questionnaire. Instead, we would let the interviewee explore, especially based on their own expertise and their competencies within the different stacks of the machine pipeline. And in terms of scope, we also tried to pick out only systems that were deployed, in the sense that we omitted systems that were, let's say, on experimental stage. So we were really interested in teams that could explain maybe the whole process from data management to deployment and monitoring of this model, and in a sense also give us a picture of sort of what pipelines they've put in place or any efforts in terms of building pipelines or on how these sort of systems are automated. And the people that we spoke to in terms of the practitioners were not limited to any role. So you could be a manager who runs a data science team, or you could be a data scientist who actually builds models, or a machine learning engineer who works in provisioning the infrastructure. Our main research questions were mainly three. We wanted to understand what's the practices that are applied in your team, what sort of tools are used for different parts of the tasks, and sort of lightly, what are the challenges that you encounter when you're dealing with machine learning systems in your own space. And we spoke to 22 different practitioners. Some were multiple practitioners from the same organization. So in total, was 16 companies were represented in this study. So now a brief walk into sort of the cases. What sort of cases were we looking at? What cases were presented to us? We had 16 cases representing the 16 companies. And we can see here that at least first, some of them were let's say, computer vision related tasks. By this could be an object detection problem. It could be form data extraction. So in the sense that you're given a picture of a structured document and you need to extract certain fields. We had speech-based systems used in different settings, let's say for transcription purposes. And in some cases, let's say using for speech UI. So this is like Alexa type of thing. We also had two systems that were MLOps, in the sense that the interviewees, their main task was to ensure that the machine learning team, or let's say the data science team, actually has all the tools required to build the product that they were working on. And then we had a fair share of systems where the main goal here is to develop analytics to support other software systems. So this is like analytics embedded within another machine learning product, but using other parts of the data system to generate analytics and infuse those into the software system itself. And then we also had chatbots represented. We had recommender systems, and generally a wide range of things you can see here. So the idea is that we spoke to very different domains, different systems, and of course the data was coming from all sorts of systems. In some cases, the data is coming from cameras. In other cases, you're using internal data collected by other systems, and so on. If we start to look at the tools across these companies, what's really used, we started by looking at storage platforms and machine learning frameworks. From the storage platform point of view, we noted that companies tend to use these public clouds for storage of data, and AWS is quite prominent, as you can see here, and Azure Cloud is also prominent for data storage purposes. In unique cases, we had companies that have to store the data on-premise because of GDPR constraints, or especially GDPR constraints. That's why they had to store the data in their own premise or their own infrastructure. If we look at the machine learning frameworks, this is quite standardized in the sense that you're either looking at TensorFlow or pretty much PyTorch, and then you're using the typical Scikit or XGBoost type of libraries to develop your machine learning software. But in some cases, you notice unique frameworks such as CALDI, which is also still used to develop speech recognition systems. And in some cases, we noticed some organizations tend to use heuristics. This is used to complement, let's say, in the sense that if you want to develop a model, and we'll maybe discuss this a bit later in the practices, if you want to develop a model and you are constrained, let's say, by regulatory concerns. So in that case, we notice that some companies do not want to use TensorFlow, or let's say they complement machine learning models with heuristics, which are considered a bit more transparent for regulatory purposes. Version control, quite obvious. This is very standardized in this space because we have Git, which is quite prominent across all case companies. But in a few instances, we did see that the company using DVC to version control their data. If you consider what tool is being used to orchestrate containers, or let's say orchestrate various containers, Kubernetes, of course, is a de facto tool here. But we did note one of the platforms, they had to use OpenShift, but then again, OpenShift still supports a variant of Kubernetes. So in this area, there is no big surprises. It's quite standardized in sort of what tools are used in this area of the pipeline. In some cases, we saw unique instances where guys were using AWS Elasticsearch or AWS Lambda to solve part of this orchestration, or part of the tool chain. The machine learning workflow. This is where it got quite interesting, especially if you consider what happens in large companies. We saw a big disparity between companies. What are people really using? If you think about the machine training workflow, there was a lot of different tools. For example, you can see Apache Airflow in this case, quite a few instances of custom tooling. And by this, we mean like these are just scripts or written, people are using, let's say, their own custom-made web tools to actually manage the training workflows and to, let's say, what's the word I'm looking for? To schedule their training workflows. Very rarely do you see these big tools such as the AWS SageMaker. In most cases, you're basically just using Apache Airflow, Argo, custom tools, but rarely did we see this use of large suite tools that, of course, tend to do everything. If you think of the experiment management part, again, quite a fair share of custom tools. People are collecting metadata. In some cases, the company is using hashing and creating scripts or tools around it. By hashing here, we're talking about you're probably collecting different artifacts from the data management part, from the model training part to the deployment, and then you create a hash around that data that you collect so that you are able to create some form of, let's say, repeatability of that process. Again, here, very different tools companies are adopting for their own use. The same thing happens to model repository. How do people store their models? Again, a very wide range of tools. You've got GCP container registries. Some are storing in Postgres SQL databases. Some are being stored in Docker registry. So the main thing here is that this sort of machine learning workflow is quite it varies quite a lot depending on what problem is being solved by the company. So by the problem I'm talking about now, is it a speech recognition system? Is it an analytics system? Is it a computer vision? So depending with the problem, then the company will choose a tool set, or let's say an approach that seems to suit them quite well. And this is sort of very different from what you see from big companies based on the literature that we've seen. The next thing is that if you think about deployment, the deployment part was quite interesting in the sense that you're looking at basically the protocols used are largely REST type of endpoints. in most of the cases, whenever there was a cloud, and this tended to be with cloud-based solutions, this would be a REST endpoint used to serve the model. In some cases, when you have latency requirements that are quite strict, we did see the use of gRPC. But then again, this is a setting where there are strict latency requirements for the model. But largely, it's a REST-based protocol that's used to serve the machine learning model. The architecture, usually it's either cloud, but in some cases we did notice there were edge deployments, and these were quite interesting, and we will maybe revisit that in the practices and how they differ between the edge and the cloud deployments. In some cases, we noticed that there were packaged applications. In this case, that we're looking at applications packaged as Shiny apps. That's when the model is developed using R. Or in some cases, the package itself, or let's say the application was packaged as a Python app. So these are cases where a model is built, but the company does not need to deploy it anywhere in the cloud or on the edge. But for business purposes, they can provide the entire thing encapsulated as an app to the business case. And these were unique to some settings where there is no product being built in that sense, but exploratory analyses are conducted time to time, and you need to package sort of this. Your analysis, you need to package the outcomes of the data science process to upstream business people. When you think about system monitoring, this was quite, I lost my slide. Yeah, system monitoring. This is quite standardized in the sense, if you're looking at infrastructure monitoring, Grafana Prometheus stack is pretty much the thing to do there. But in some cases, we noticed that companies are quite interested in very low level metadata that's coming out of different parts of the stack. And therefore, there was a lot of logging of tools, logging of systems, very low level. And they would then use this data to, of course, either present it in a web tool or just store it in a database for further analysis. So again, this in terms of monitoring, it's pretty much standardized. You're doing either infrastructure monitoring, but we will see later in the practices, when you want to do model monitoring, it gets a bit tedious, and the tooling there requires a bit of heavy lifting. That's basically when you're looking at different parts or types of models. So now into the practices and challenges. When we talked about data management, and here we're looking at data collection all the way to, let's say now you have some features. What we noticed is that in one case, let's say depending with the model you're looking at, let's say here we're considering vision, speech type of systems, this collocation of data and compute related tasks in your pipeline are quite important. This allows the data to the model training to, you sort of save some time from the model training part. If you have collocated your data and the compute nodes, I mean, they share the same nodes. So these are, you reduce the latency if you had stored the data in an external storage system. And of course, that has economic sort of bearing to the training time. If you think about the data sets, we did see some cases where companies have abstracted the data. This is where it is possible. Think about structured data here. So we saw some companies make some effort to standardize the data set, the standard data interface. So you're looking at Apache or NetCDF. And in this setting, the data scientist just needs to ensure that their model can consume an Apache packet and it can emit an Apache packet. So that allows the platform team to provision a system that it sort of abstracts the work for the data scientist. And it decouples the work, the data scientist team and the platform team quite neatly, in the sense that the platform team does not need to know or care what the model is doing as long as it can consume these sort of abstracted data types. In a certain case, we also noticed this documentation of data, and this bears in large organizations where there's a lot of data in different parts of the organization. And data scientists tend to spend a lot of time trying to figure out what data is useful really to create certain models. And so there was an indication of this need to create a data catalog so that it would reduce the amount of time data scientists take to discover data and to actually identify its value. This again speaks to very large organizations. It's not a situation we noticed with small companies, which the data is very well known among the team. But in very large organizations, there's a lot of unique data sets in different parts of the organization that need to be well documented for use in machine learning systems. Validation is quite common, but different techniques are used. And validation here, we did notice that in some organizations, it takes place at the data level and also at the schema level. And somehow it was seen important in one organization to separate this role, who actually is in charge of data quality, who manages the schema, and who is in charge of the validation efforts if they do break. So in this case, there were some data stewards who are appointed to ensure that data is always in good shape and in the right quality, and the schemas are up to date, and they actually don't fail through the validation process. And this then allows the data scientists to be more productive and focus on tuning the models and so on. So what about the challenges that we found out, or some of them related to data management? This issue of data quality did stand out as an interesting problem, especially in large organizations and in settings where you have bought data from third parties. It takes a while to figure out who is in charge of certain broken scripts, or let's say broken schemas. So this is sort of an open problem in most of the organizations. Who should be in charge of data quality? Because data scientists have this feeling they spend a lot of time trying to actually put data into the right shape. And in some cases, it tends to break even their pipelines if they haven't been paying attention to nitty-gritties of the data quality. In IoT settings, this is quite obvious. Sensor outage, latency, low traffic priorities in some of the 4G networks. These are some of the things that tend to affect data quality in certain organizations. As you ingest the data, you're sometimes never sure whether the sensor collected the right data. And so it means you have to put systems in place to actually validate and check whether, what you get is what you expected. And of course, we have the good old programming problems, which bugs in the software that are used to collect the data. This can be quite subtle and can be quite problematic to identify in some of the cases. If you now move away a little bit from the data collection, now you have data and you have features in place. One thing that was mentioned was this lack of standardized annotation across neural networks. If you're considering moving a model between a RESTnet and a VGGNet, for example, it might be that the annotation format between these networks does not render itself so in such that it's standardized so that you would actually just move your code into a different system and it would work. It always maybe requires you to write a script to label the data to match sort of the network that you want to use. So these are some of the things that were raised in terms of data management challenges. If we look at the model training and the evaluation of models, of course, we did notice that transfer learning is quite a popular approach. And why this is popular in some cases, of course, it does allow you to avoid a cold start when you're building a model and you don't have enough data. But we did notice that there was sort of this dichotomy between public versus private models. In some settings, companies have trained, you sort of train your big model, let's say 2 weeks worth of training, and then you use that model to conduct transfer learning within your other models. And that has an effect of allowing you to save costs on one part, and largely save costs. And on the other hand, you also then have, let's say, if you have quite enough data, then you have a model that's a bit more relevant and well-tuned to your business case. So in the sense here, the point is that when you consider transfer learning, organizations also have this way of approaching these things that it doesn't always mean taking a big model from the public domain. It means that you could also train your big model and then use it as a baseline to conduct other transfer learning, subsequent learning. When we talked about heuristics earlier, I already mentioned this. This is usually used in a way to complement machine learning algorithms. In this case, what was apparent is that you may have a model, a machine learning algorithm that is very accurate, but for reasons that are, let's say, regulatory driven reasons, you cannot fully explain how the model actually arrives at that decision. It's not that you cannot explain as a data scientist, but to the business setting, the algorithm is not as transparent as what the regulatory constraints may require. So for that reason, some of these companies have opted to sacrifice or trade off accuracy for explainability. So this was something that was quite, at least unique from a data scientist point of view, that it's not always the accuracy that is carrying the day, but explainability of these models is quite important. When you think about the choice of framework, and in terms of how do data scientists choose this framework, for example, why do you use TensorFlow to do a speech learning system or a PyTorch compared to Kaldi? So we did notice that practitioners, they value flexibility quite a bit. And depending with exactly what you're looking at in terms of what problem you're really solving, then either of these frameworks can be used. But what the teams tend to do is some teams really prefer low-level access to the components, so that, of course, they can extract a lot of metadata, as we saw in the machine learning workflows. Some teams really prefer to get a lot of, the more metadata you have, the better it is when it comes to debugging your system. So that's the main point here. Then again, another thing that came up when you're looking at training models, how do they evaluate the quality of the models? It's typical, of course, you can carry out these cross-validations and so on, but we did notice one setting where the company had organized its own data sets based on quality. So this allowed them to actually test how the model performed across different types of data quality. And so in this way, they could tell, how well a model would generalize across, let's say, different data sets. What problems are associated with machine learning, more model training and evaluation? The ones I've picked here is mainly model benchmarking, the cost of model training, and explainability of model. By model benchmarking, the main problem here is that when you're building a model, remember we started saying that when the big companies create models and they publish them, usually it's almost impossible to achieve the same model, or it becomes almost impractical to benchmark against the model. So this is sort of an ongoing issue here, that how good is your model relative to what is the best out there. And when you start to think of what's best out there, then you realize it's almost not practical to replicate it. And so there's this, you sort of end up coming up with your own benchmark. And then again, is it the best it can be? So it's an open question right there. And of course, when you're playing around with very big models in computer vision, or let's say in speech recognition, NLP systems, the cost of training models starts to become a hindrance or a barrier to experiment through the experimentation process. In some cases, we've seen companies, one way of managing this is deploying, or let's say provisioning their own infrastructure internally. They've bought this hardware that comes from Google. I'm forgetting the name. So they have sort of this, GPUs. They have GPUs deployed internally so that they could actually manage with this cost of training the models. And explainability of models, I've already mentioned that. This is sort of an ongoing open question. How do you explain the model? It's very accurate, especially for neural networks, but is it explainable to the extent that the regulator would be happy with what you're doing with your machine learning system? When you think about deployment and sort of the practices here, we did notice when these companies are doing, let's say, creating servers that would be used for inference, I'd say almost 90% of them are based on custom servers. We did probe one to ask why Why is it they have not opted for off-the-shelf servers? In some cases, the servers were not available by the time they were starting to build the system. In another case, the practitioners expressed that they prefer to build the servers themselves so that they can collect probably more metrics that they want, and they can also package the whole thing in a Docker container according to them. So they get more flexibility, let's say, with the server according to that practitioner. And when you compare the edge and cloud systems, what's the main difference in terms of deployment? It seems that cloud deployments are very straightforward. The practices carried forward from software engineering help in this case. But when we consider edge systems and machine learning in edge systems, it did look like the tooling and the frameworks and sort of the organizational settings required can be quite daunting, especially when you have to iteratively update models in the edge. So this is an interesting area, even in terms of research, and I think that it renders a lot of open questions beyond the scope of this paper. In terms of monitoring parts of the pipeline, we did notice there's efforts to monitor the quality of the data. We also noticed there are efforts to monitor drift within models. And if you think about monitoring infrastructure, we said Prometheus stack is quite straightforward. But when you look at the tooling around data quality monitoring and model drift, this is still an area that is under development, we would say. So this, of course, raises some interesting challenges in the sense that if you're monitoring a model, in some settings, because of GDPR, or let's say because of how you've deployed your model, it's not always very straightforward how to monitor for model staleness, especially in online deployments. So this is not when you're doing batch predictions. This is when you're doing online predictions. This can be quite not so straightforward how to do this, especially if you're working in a constrained environment. Pipelines. So now when you look at the big picture, now you have your model, you have your data workflows and everything working, and you want to automate the entire thing. There was a lot of effort across the teams to consider version controlling everything. Any artifact that's produced across the process, we did see companies making efforts to version control everything. So that also creates a lot of transparency and within the pipeline. And in cases where you have infrastructure as code all the way to a deployable container, then we did notice that there was quite good automation workflows within the organization. And companies also try as much as possible to put everything in containers. Data workflows, machine learning, training, deployments. If everything is within a container, then the scalability of the pipeline becomes quite natural with tools like Kubernetes and so on. And so some of the tools we noticed that are used for workflow automation, we did see there's a lot of custom tools, but there is also dedicated tools, for example, Apache Airflow, Argo, Kubeflow. These are some of the tools that teams have either adopted or have recognized that they probably need to adopt to facilitate the orchestration of their pipelines. So what are the problems there in machine learning, in machine learning pipeline management? How do you maintain the entire stack up to date? So this requires quite rigorous testing practices that in some cases are not in place, but teams are aware that they should put this sort of, let's say, practices in place, but usually we see it as an area of big development across most of the teams. And of course, the pipelines themselves can be quite complex in the sense that then they require somebody who is very well tool skilled to be able to run this. And in terms of skills, of course, as I mentioned, you need to be very highly skilled to be able to do this, run pipelines end to end. So as we conclude, what did we really observe, or sort of the findings we made as I've listed here? So streamlining data handling procedures can be quite challenging. And here I'm looking at different types of machine learning tasks, from vision, speech, NLP. it's very challenging, especially an organization that has multiple products based on machine learning. Machine learning the model explainability is still an open area. We don't see a lot of tools yet that support this part of the workflow. When you think about bias, when you think about feature attribution and so on, we still don't see this being part of the practices directly, at least across all the cases. But practitioners are well aware of this, but I think it's a case of tooling being not, let's say, mature enough or well integrated enough to the kind of tools that are already being used by the practitioners. And we did notice that there is this sort of aversion from very big tools. And just to put a name to it, I'm talking of a tool like SageMaker. And practitioners here tend to trade flexibility for these sort of huge integrated tools that tend to do it all. So practitioners want to use a collection of tools a tool that's really good in what it does, but then have multiple tools to do that. And then it's sort of a vicious cycle. Then when it comes to maintenance of your pipeline, it also now has an implication because it adds workload in terms of maintaining the entire pipeline. If you think about portability, we did see that when you think about portability within computing environments, this problem is very well solved with tools like Docker. If you think about portability within frameworks and models and algorithms, how they work in different settings, this is a big contrast compared to what large companies do. So the companies we spoke to tend to use one framework for their research purposes and for their deployment purposes, and let's say production purposes. But in large organizations, we see, or let's say the literature indicates that very different frameworks are used for the research purposes, for example, PyTorch. And then they would get into an intermediary state where they use ONNX, that's ONNX, to create now customized production machine learning production models for their own custom, let's say, hardware. So this is one big difference that we noticed between the entire environment, between large companies and, let's say, the case companies that we spoke about. And I think that sort of concludes my talk, which I've taken already maybe more than the time allocated. But I do welcome you all to please look at our paper, which goes into much depth in this sort of discussion. It's still in preprint stage, but please take a look in this preprint server text driver. Yes, thank you very much, Markus.
Okay, thanks a lot for the very interesting talk. So we now have still a lot of time for questions. So I see Anna has raised her hand. So Anna, please go ahead.
Hey, Dennis.
Yes.
So how would you say what is the biggest problem for all these companies implementing machine learning, if it's one problem in one sentence?
I'd say if I choose the problem, which is what I see, is data. Data handling is a bigger problem. Everything else they can figure out and manage with it, but some of the data sets just render themselves challenging to work with in terms of validation, in terms of ensuring that it's the right quality. So I'd choose data management as a bigger problem.
You mean both data quality and amount of data?
Yes.
Thank you.
Yeah.
Okay, and then Nuutti has a question.
Hello, thank you for the presentation. This was super interesting. Did you you interviewed quite a lot of companies, but I'm from city of Helsinki, represent the public sector. Did you have any like interviews with any like non-profit organizations?
Yes, those were represented. I'd say one. There was one case where the company, the interviewees were from a public institution.
Yeah. Did you see like any difference between these two like
yes.
private sector and public sector?
Yes. So, and the difference being that they are not at the liberty to use public infrastructure as, let's say, any other company would easily do. So that complicates their day-to-day activities, because it's not as easy as just thinking of an idea or an experiment and then running to AWS and executing it. This requires, in those settings, because of course of citizen data, even access to the data itself within the organization can be quite problematic from how we understood it.
Yeah,
So,
yeah, that sort of resonates our experiences as well. Yeah,
yep.
Thanks.
We have a question in the chat. So Elena has a question. Elena, would you like to ask it yourself, or should I read the question? Okay, so Elena asked in the chat, so for the tables listing tools used, for example, the version control and orchestration, does the sort of the straight line indicate that there was no capability or that was not applicable?
Is that the interviewee did not directly say what they were using. So of course they're using something, but we did not want to put words in the interviewee's mouth and say this is what they used, even though we could infer it. If they did not say that they used it, we didn't put it there.
Okay, and any other questions? I have one question. So
yes, please.
I wonder, do you think that sort of the complexity of the machine learning task affects things? And did you see sort of differences in this? I would assume that some organizations have relatively simple tasks and then some might have very complex tasks.
Yes, absolutely. For example, if we consider companies that were building speech systems, computer vision systems, inherently their pipelines were very complicated. That's because the data itself is unstructured and it's very large data. So yes, the answer is that yes, it was quite clear that some settings the problem was quite straightforward and how to solve it. In certain settings, especially vision and speech, the systems were inherently complicated. Yeah.
Okay, thanks. Timo has a question.
Hi, yes, thanks for a very interesting talk. I actually work in the industry at the moment in a large Finnish company, so it was extremely good to hear some peer practices. I started wondering, did you explore, does it affect your results, especially in respect to the MLOps tooling? Who owns the IT infrastructure and who builds the data science systems? For example, if the public cloud infrastructure of the company is owned by a centralized IT, and then the data science things take place in different business units.
Yes, there was, I'd say, let's call them even organizational issues that were popping up. Why and how this came about is that if the data scientist is not involved in infrastructure related stuff, most of the time that's where this yin and yang of the data quality came up. So the data scientists expect the data to come in a certain way, and the platform, the people who manage the platform, let's say the IT people, maybe don't understand the requirements of data quality. So there is always this issue of then who should take care of this quality. So yes, depending on how the company is organized in terms of supporting data science teams, then when they're too separated, then issues of data quality and ownership of things became a challenge. And how some of these teams solved it is using these abstracted data sets, as I mentioned. So Apache Parquet, NetCDF, at least that's what they did to sort of standardize sort of the data interface. But I'm aware that it's not possible in all settings. For example, if you have structured data, you can use Apache Parquet. But if you're looking at video and images and documents, then this is not quite straightforward how to solve that. So that's where this whole idea about getting a team that's dedicated to ensure data quality is observed comes about.
Okay, I think we are now running out of time, so let's close this session. So I want to thank the speaker again, Dennis, for a really interesting talk. I also want to thank the audience for your interest. And next week we continue with a talk by visiting professor Roderick Murray-Smith. So have a nice day, everyone.
Thank
Bye.
you. Yep.
Yeah, thank you, Dennis. That was really interesting. And you had a big audience also, so that was great that people also noticed the topic.
Yeah, there was almost 50 people here.
Yeah,
I think this was our record from this autumn season.
Definitely. Yeah.